Hello, and welcome to the third episode of the Sienna training series. I'm Kate Doubleday, and I'll be introducing a little bit about how Sienna Ops works. So Sienna is an open source ecosystem for power system modeling, simulation, and optimization with three main applications. Sienna Data for inputting and transforming energy systems input data. Sienna Ops for system scheduling simulations. This includes formulating and solving optimization problems like unit commitment, economic dispatch, and optimal power flow. It also supports sequential simulations for production cost modeling. The third application is Sienna Dyne, which enables system transient analysis, including small signal stability and full system dynamic simulations. All three applications were developed to support modeling with large shares of inverter-based resources like wind and solar. And today we'll be focusing on Sienna Ops. So each of these three applications is enabled using a combination of packages written in the Julia programming language. Sienna Ops includes 7 packages currently, but these applications are always under development. So these 7 packages include some overlap with the other applications. Power Systems, which we introduced first in the Sienna Data video, is used to parse and format input data. Power Simulations is the sort of foundational package within Sienna Ops, and it's used to formulate and simulate scheduling problems. There are 2 extensions to Power Simulations focused on the extending the formulations available for hydro generators and energy storage systems. Power Flows, like it sounds, is a package to calculate simple power flow problems. Power Analytics is a post-processing package, so this can help to analyze simulation results using common metrics. And Power Graphics can be used to visualize data inputs and key results. So Power Simulations and its relationship with Power Systems is really the main focus for this introductory video. We introduced this overview to Sienna's approach to formatting data and models in the Sienna Data video. So as a bit of a review, there is a separation in Sienna between the data for a model and the equations that describe behavior. So within Sienna Data, you can input data into consistent representations for different components and store that information in memory. Today we'll be focusing on the second half of this approach, which is using Sienna Ops to formulate the behavior. So to describe problems like power flow, unit commitment, and economic dispatch, which can then be combined with the input data coming from Sienna Data to develop a complete model, both data and equations that can be sent to a solver or simulated. So there are a couple of key concepts within Sienna Ops that we want to introduce: formulations, templates, and decision models. And we're going to use the analogy of making a robot walk. So in this case, the robot is our data set. This contains all the information about all the components in our system put together through Sienna Data. So a robot has arms, it has legs, it has a head. And if we want to make this robot walk, we can define behavior for the different component types. So let's say if we want to walk, we'll have each arm pump and each leg stride. And we call these formulations. So this is describing the behavior for each group of component. When we put these instructions together, we get a recipe that we call a template. So we can have a walking template that describes the behavior for each group of components. And this doesn't depend on the data. This is just a set of instructions. So we could define different templates. We could define a dancing template in which we have our arms wave and legs jump. And we could apply either of these behavior templates to a robot. So in our analogy with power systems, the 2 most common templates we might talk about in power simulations are a template for a unit commitment problem or a template for an economic dispatch problem. So back to our robot. At this point, we've defined a data set, and we've defined a set of instructions. And once we combine them, we have what's called a decision model. So a decision model is a complete optimization problem with data and equations that can be built and solved, and which gives us our final results. So you could think of this as uploading the instructions to the robot and actually seeing it walk. And at this point, our analogy is sort of completed. Under the hood, Sienna uses jump.jl, which is a modeling language for mathematical optimization embedded in Julia, to build the optimization problems. Both open source and proprietary solvers can then be used to solve the problems in JUMP. So to review, in Sienna Ops, we first import data using Sienna Data, using powersystems.jl to define a data set. We then use powersimulations.jl to define a behavior template, which includes the formulations of behavior for each type of component in the system. We then combine the data and behavior to get different decision models that result in different outcomes. So that could be, for example, applying the same behavior to different systems that result in different outcomes, or it could be in applying different templates to the same data set. And that's kind of the benefit of the modularity in Sienna of separating these two items, data and behavior. Once we've completed a simulation, we can analyze the results with Power Analytics and visualize the results with Power Graphics. So for next steps, we recommend familiarizing yourself with the powersystems.jl documentation, and I'll show that in a moment, including the formulations library. If you're interested in a code demo, you can watch the episode on Sienna Ops operations problems, where we'll step through those steps of looking at a problem template, building a decision model, and solving it. So just to conclude this video, we'll take a look at the Power Simulations documentation. This is linked in the video description. It includes some overview information and various guides. And at the bottom here, there is a formulation library. So this includes some introduction to seeing how behaviors are formulated as mathematical equations in Power Simulations. And you can also look at different component types and see the available formulations that are included that you can use in combination with other component formulations to define a template. So we'll leave it there and look forward to seeing you in the next video. Thanks very much.